Good morning, good afternoon, everyone. Welcome to Altium Live 2022 Connect Conference. My name is Sarmat Komoro. I'm the Vice President of Business Development for Electronic System Design from Altair. In today's presentation, I'll be talking about how to ensure electronic system design reliability and how the EDA industry addressing it. Companies like Altair and Altium, how they are working together to address the challenges of electronic system design reliability. So let's get started. We are living in the digital age now, and digitalization changing everything in our life. We are experiencing this today. The way we design things, the way we manufacture things, the way we use things, the way we communicate with people, interact with people, everything became affected by digital age. The center of this digital revolution and digital age, it's electronics and electronic systems. We are here in this conference because we all involved in this electronic system designs. We are involved in the digital revolution. The next few slides, I'll be talking about the industry trends, start about the industries, what's going on with the electronic systems, and what kind of challenges we're seeing and how we're addressing it. So, electronics is one of the fastest growing markets. It's actually affecting many industries. If you look at the aerospace and defense, consumers, medical, automotive, these are four industries experiencing growth due to electronic content in their products. I'll have some stats to share with you about some of these industries. For example, the global consumer electronic market is expected to grow by over 7% year over year to achieve $1.5 trillion by 2026. If I move to other industry, automotive industries, vehicle electronics will reach more than 50% of the car content or car value by 2030. Another example of an industry maybe close to us in this conference, we contract manufacturing, people involved in developing and manufacturing circuit board, PCBs. This industry is expected to grow at 9.5%, 9.4% year over year to achieve $730 billion by 2027. That's a huge market. These are public information. You can look at it from different research firm. So you see this stats, three industries, other industries like industrial, building technologies, transportation, heavy equipment, they're all experiencing the same growth due to electronic content in the product. Electronics, it's happening at different levels. So let's look at the levels. Electronics happening at the chip level, IC design level, IC, PCBs, which is the area we are involved with here. We're talking about it in this conference. Subsystems, also an area electronic involved. System level, where you have, could be the car, could be the plane, could be the big rack, a box that have multiple subsystems. And the last level where electronic also exists is a system level, where you have, for example, car-to-car communication, car-to infrastructure, maybe satellite to base. These are different levels. Each level has its own challenges and has its own requirement and has its own issues, its own trends. There's a need to have integration between these levels. There's a need to have interaction between these levels, between all these levels. In this picture I'm showing you here, from a chip to system, there's a terminology or there's a term that is used in the industry now called chip to city. You may have heard that term before. Electronic exists from the chip all the way to the city right now. Now let's talk about two items on this picture right now. the PCB and the subsystem. This is what consists electronic system design. The next couple of slides, I'll talk about the trends and challenges affecting the PCB and the subsystem, electronic systems designs. We're not going to be touching on the chip. We're not going to be touching on the system and subsystem. So look at the electronic system trends. What's going on? Electronic systems, which is really consists, could be a PCB, multiple PCB, an enclosure, they're getting more complicated. Customers, our customer, your customers, most likely asking for more functions and features. The design getting smaller. The packages of the components getting smaller. They're getting more complicated, more layers, more dense. So a lot of advancement in technologies, a lot of new protocols, new maybe challenges in manufacturing. So getting complicated every day. Another trend we see, because of the complexity of the system, there's a growing cost and there's a growing timeline. So, of course, our customers are always asking us to have the product faster. If you're designing a console, game console or cell phone, companies like to get them out before the holidays so they can capture market share. So there's a challenge and there's a trend to get it designed faster, getting the product faster. Of course, it put a lot of pressure on companies on timeline and cost. There needs to be some trade-off between getting it faster, cheaper, and better. Of course, you need to have it high quality also. You need to have a reliable product. Another trend we see, it's a compliance mandates. Many industries now have their own internal mandate, their own compliance mandate. For example, if you are in the automotive industry, if you're designing any control unit that maybe goes in the car for autonomous drive or maybe EV, it may have something called ISO 26262. It's a functional safety requirement. If you're developing a medical device, it may have its own medical industry requirement. If you're developing industrial equipment, electronics, it has its own requirement. If you're developing an electronic board that goes in the maybe in a satellite or in the plane, that has its own requirement for a flying electronics. There's something called the DO-254, which is a flying electronics requirement. Of course, companies developing electronics, they have to certify their designs, certify their product according to this requirement. So there's a challenge, there's a trade-off have to happen between cost and further risk. Now let's jump into electronic systems challenges. So look at the trends, let's look at challenges. Electronic system, from its name, is not electronic by itself, it's a system. It consists of multiple disciplines, multiple domains. There's electronic domains, mechanical domain, software domain, and electrical domain. These need to talk to each other, need to interact with each other. Each domain has its own requirement, has its own challenges. The integration of electronics, chip, package, PCB, into the mechanical, to the software, to electrical, traditionally very challenging, a lot of issues. And most likely, they're siloed. The teams are working in these domains are siloed. There's a need to have integrated system. You need to have integrated system simulation. These domains need to talk to each other more often. The lack of integration and collaboration between these domains can lead to longer design cycle, late process testing. Also, can lead to more cost, increased cost, development and product cost, and also decreased quality. And of course, increasing time to market. So these are challenges for people developing the systems. Let's look at the challenges from people's standpoint. So look at the evolution of people involved in designing electronic system and the challenges. Back in the 80s, designing a PCB or designing electronic system can be done by maybe 2 or 3 people. You have a double E, you have the layout engineers or drafter, you may have manufacturing engineers or maybe a mechanical person. Sometimes maybe the layout engineer is acting as a mechanical engineer. In the 90s, more people get involved. Maybe with the introduction of PGAs, and now you have the maybe signal behavior after study. So you have the signal integrity engineers. You have a complicated component library. You have to have librarian person involved. So now you have more people getting involved in the designing electronic systems. And the challenge now to have all these people talking to each other seamlessly. Fast forward to 2000 and beyond, now we have more people involved in electronic system. I'm showing you some example of few of the people: the mechanical person, the software engineers, the wiring engineers, the quality engineers, thermal engineers. There's also non-engineering people get involved in the design, believe it or not. The procurement, purchasing, sometimes salespeople in the company, they may actually get involved and give you a requirement. Marketing people get involved. They give you feedback. So the challenge is to have all these people talking to each other. The challenge to have all this domain connected. And other challenge we see right now, companies can't afford to have a specialist, cannot afford to have thermal engineers on the staff or EMC engineers on the staff. So they would like to have their electrical engineers or maybe their PCB designers or the system engineers start doing some of this analysis, some of these checks, validation, and tests themselves. So they're looking for help by providing a solutions to them that not a specialist solution. We need to have a solution to be used by the, we call it maybe the average engineers or the average designer. There's somebody only doing layout or doing schematic, be able to do maybe some of the testing themselves using some applications, some tools. Now let's look at the technical challenges of the electronic system design, or PCB in this case. Most of you guys may be familiar with this. I don't have to repeat it, but you can see, of course, the density of the design, getting dense, mechanical enclosure, the speed of the signal, the component technology has been used, the thermal effect, the environmental conditions like vibration, acceleration, material technology, what material used in the PCB stack-up, for example, what material used on the enclosure, as a plastic or metal, manufacturability, can I manufacture my design in-house? Can I outsource it to maybe contract manufacturing, let's say Mexico or China? Does the manufacturing partner have the ability to build and assemble my board? Of course, the cost and schedule is always important. If you are a high volume company developing, manufacturing a lot of your product, it will maybe thousands, maybe hundreds of thousands. Cost and schedule will be very, very huge to you. And also depending on the industry. If you're aerospace and you may have different requirements or different challenges than automotive, maybe you have different challenges than medical. So these are some of the common ones across the maybe PCB industry. You may see different ones in your specific industry. Of course, most of us involved in developing electronic system would like to have our system reliable. The cost of a reliable system can cause to failures. Now, let's look at the why system fails, why electronic system fails. They can fail due to different factors. Design factors, could be component used, could be EMI interference, could be signal and power, could be thermal, could be the packaging of the design, the component packaging used, could be environmental factors, excessive heat, humidity, moisture, vibration, stress, bending, aging. These all environmental could be factors. Another factors, manufacturing factors could be the assembly fault, fabrication, solder fatigue issues that can cause electronic system to fail. So what companies developing electronic system doing typically? They try to test in the lab. They try to test in the chamber. They try to test in the field. Most of us try to do that. So as I mentioned, companies rely on prototype and physical testing, but reliability problem does not show up as a quality issue in manufacturing during the product design and during product manufacturing. So a system can pass manufacturing, but it still fail in the field due to some stress. Also, you cannot test component and PCB assembly aging in the lab. It's hard to do that. Creating a prototype and testing does not always work. You may be able to test a prototype for some acceptable errors, maybe some acceptable failure rate, but not for everything. It's also hard to simulate tests and or maybe simulate year of stress in test chambers. An example, if you're developing an electronic unit that goes in the car or maybe in the plane, that the product have a longer life cycle, it may take you years to do field testing for that product to achieve a reliable product. So it's you may have to drive the car maybe millions of miles to get all the test scenarios to see if the system will be failing or not. So the more prototype, the more testing will increase your time to market, will increase your cost. Companies have issues with reliability. A lot of companies get affected by non-reliable product. An example, the cost of non-reliable product, here's some example for 3 companies. One of them actually, or 2 of them actually, consumer electronics. One is a medical here, where actually they have major recall due to some unreliable product, maybe due to heat, due to maybe some electronic issues, can be due to some mechanical issues in the design. So what's companies looking for? What are they looking to do? What's the answer to this? What's the answer to achieve a reliable and robust electronic system design? The answer is adopting what we call a digital twin, a digital model of your design. So digital twin in the context of electronic system design is the virtualization of the development and design process. Taking your lab testing, field testing, shifting it left. Do more simulation upfront. Do more analysis and verification on the front digitally. Developing a model of your board, of your design digitally, work on it digitally before creating any prototype. We call this in electronic system design, we call it simulation-driven design. So the answer to achieving a robust electronic system design is adopting a simulation-driven design process. What does that mean? What's a simulation-driven design process? It's a solution can predict reliability issues to help avoid design practices that can cause failures. Really, ability to simulate months and years that you can do in chambers, do it now virtually. Predicting failures, product failures in hours. Improving the design quality by integrating verification throughout the design, not at the end of the design. Finding the problem early by automating best practices. One of the most important things of the solution of doing simulation-driven design, offloading domain specialists by moving some of the first-order checks and verification to the design engineering team. For example, if you are you have a thermal engineering staff or EMC engineering staff, that person will be very, very busy. He can offload some of his tasks into PCB designers and doubly by adopting a simulation-driven process. Here are some examples of this PCB design, virtual prototyping. We call it simulation-driven design applications or needs. Signal integrity is one of them. Power integrity, electrical rule checking, thermal management, thermal simulation, vibration and shock analysis, of course, DFM and DFA, design for manufacturability, design for assembly, validation. These are some examples of simulation-driven design process that apply to electronic system design. The next few slides, I'll talk about solutions. What does companies like Altair provide in the area of simulation-driven design for electronic system design? Quick history on Altair. Altair has been in the industry for over 35 years as a mechanical simulation and analysis company, started in 1985. In the last few years, last maybe 7-8 years, we've been heavily involved in the area of electronic system design, simulation, and verification. as you see from this slide, we have different elements that apply to electronic system design. It starts from electronics, pure electronic. This is the PCB area, where we have a solution that covers PCB design review, verification, analysis, manufacturing. The solution called Pollux. We'll be covering this in more detail in the next slide, but also one of my colleagues, Harry Kennedy, he'll be presenting more detail on the solution with demos, and also he'll be talking about the integration with Altium, how this solution works with Altium Designer Flow. The second part, or the second element of the solution, is the electrical, where actually we can simulate and optimize wireless networks, wireless connectivity. We can do EMC, EMI, system level analysis and simulation. We can do antenna design and placement, part of electrical systems. Part of also electrical system design solution, we have mechanical and thermal system level analysis for the PCB or the enclosure or the subsystem, where actually we can simulate in one environment mechanical structures on the PCB, vibration, acceleration, solder fatigue, electronic cooling. It's all in one environment. Moving to the right, and the mechatronics, we have an environment called the Flux that allows you to do motor design, mechatronic design, and simulation. It also can connect to other solutions we have from Altair. Also can connect to other solutions from partners. The other part of the solution is the circuit simulation. This is a spice level circuit simulation that's actually integrated in some of our solution in the electronic and electrical, but also exists as a standalone simulation tools. Last but not least is the code generation out of part of our electronic system design. We have a tools can allow you to create visual representation of your code that actually can go to program a microcontroller that goes in a PCB. We'll talk about that in more detail. Our solution is supported by an HPC platform and also a cloud solution, cloud accessibility. Let me cover some of these solutions in more detail. Hopefully give you a flavor of what we offer from Altair to address electronic system design challenges. The first part of the electronic system design solution is the electronic part, which is, I'm referring to electronic PCB design or PCB itself. As I mentioned before, designing PCB requires multiple people with different disciplines involved in the design. You have the electrical engineer, the PCB designer, mechanical engineer, manufacturing engineer. You may have EMC expert. Of course, you may have the management team. These all involved in the process, maybe in the design process, but also involved in the review process. So they all need to collaborate. So having a solution that integrated with the current EDA flow is very essential for these guys to work together. In this case, a solution like I'm showing here can help users do that. Another area, when you design PCB, you have to manufacture it. So taking the board, sending the data to your fab house to fabricate the board. Typical fab house, they will have a set of rules. They need to check the board against to make sure the board that can be fabricated. And these rules, typically, they vary from customer to customer. They vary from industry to industry. For example, if I'm a automotive customer, I may have different requirements for my PCBs than consumer electronic customers. So if I can do this checking early in the design cycle, done by the PCB designer, or sometimes by the engineers, it will reduce the time I have to spend in testing in the manufacturing phase. It will make sure I can send a data to my manufacturing with less errors in them. So I can fabricate the board faster. I can reduce the amount of spins. I can reduce the amount of scraps I create. Of course, assembly is the same thing. So if I can do some checking for my assembly during the design process, it's very important. So, because if I'm doing captive manufacturing, that means I do my own assembly or I outsource my assembly, is the same thing. There's assembly rules that typically manufacturing engineers, they have to follow. The way the placement of the component on the board, if it's a manual or automated, the rotation of the component. There's different rules that can be applicable to assembly. If I can do these checks during the process of designing the PCB, so I can put manufacturing and assembly in my head as a designer before or during the design, it will help me save time at the end. The last part of doing checking is really electrical checking. So when we design PCB, you have to make sure it's going to be functioning as designed by the electrical engineer. So finding errors in the design related to electrical behavior, for example, the way I'm routing my traces on the board, it may cause some electrical bad behavior. For example, I may create a loop antenna on my board that may cause a common mode emission. If I'm routing high-speed signal to the edge of the board, or maybe if I'm placing component like a capacitors or decoupling capacitors far away from a pin, it will be ineffective capacitor, for example. If I'm routing a trace with multiple vias, I'm creating maybe a longer trace. Some of these electrical checking or electrical rules can impact the behavior of the board. If I can find these errors early in the design cycle, it will help me save time also. So these are three types of checks can be done. Design rule checks done in the PCB. If a design engineer or PCB designer can apply during the process. Also, when we design PCB, typically we try to test them in the lab. Do kind of maybe signal integrity test, maybe doing a probing on the signal to make sure I'm getting the right data. Well, we're shifting and left. So as a design engineer or PCB designers, I want to test my design virtually. So doing testing like doing crosstalk analysis, undershoot, overshoot analysis, doing, for example, differential pair signaling analysis, DDR analysis, doing S parameter extraction. It will help me find errors early in the design before even fabricating the design, before even maybe sometime before we even starting the PCB layout itself. The same thing with power. If I can do some quick analysis like AC analysis, noise analysis, if I can do decoupling capacitor optimization or analysis during the design, it will help me maybe choose the right capacitor. It will help me choose the right value. It may help me choose the right placement and maybe routing to the capacitors. And last but not least is thermal. If I can do some thermal analysis on the board to see which component generate more heat than other area. If I change my placement of the component on the board, what kind of impact I'm going to have on the PCB itself. So if I can do this analysis quickly, early, it will help me reduce the time I spend on the lab. Of course, people can do some of these with different tools, but if I can provide the user community one solution can do all of them in one application, that's a huge value. So here in this case, the electronic solution for PCB from Altair, actually it's one application that can allow you to do all this kind of stuff. Design review, rule checking based solution, and also simulation analysis for signal integrity, power integrity, and thermal at the board level. The second part of the electronic system design solution is the electrical part. Of course, PCB, they may go in an enclosure. For example, if it's a car, they go in a box, and you may have multiple maybe units, we call them ECUs, connected through cables, maybe harnesses. And you may have antenna on the car, for example. In this case, you can study a system level EMC where you have an impact from board to board through cable. So there's a problem, for example, maybe one board emitting and maybe other board may be a victim through the cable. You can do analysis on this scenario and study the behavior of one board to other board kind of interaction. Of course, if you have an antenna used in this case, you want to see the impact of antenna on my PCB, what kind of radiation am I having here. The solution goes beyond that, beyond the PCB only. It actually would cover other area that I'm not touching on here today because it might be, we call it, has value to you guys, but it's an area that the Altair will focus also on. What comes to thermal, I covered the thermal on the PCB itself. When I talked about PCB can be scanned for any hot component on the board, the way you place it and so on. But of course, the PCB, it can go with other PCB in the box, and that box enclosure, or could be let's say an ECU, or could be any box, could be an LRU that goes in a plane that could be placed in a hot area, for example, or maybe the product that you're designing, your customer maybe use it maybe in a very hot environment. So studying the behavior of the system, or even the PCB that goes in the box in the system, to see what's going to happen from a heat standpoint. Study the complete electronic cooling. Study the impact of maybe the fan you're using, the airflow, the heat sink, the type of enclosure, the slots you're creating. If I'm a mechanical engineer helping the PCB designer creating a slot on my enclosure to provide cooling, what kind of slot I have to create, the size of them, the location of them. This is very important. So solving a problem related to conduction, convection is very essential for doing electronic system design, cooling. In this case, talking PCB or multiple PCB in a system. Of course, this needs to be easy to use. So the solution here does not require a CFD expert. You don't have to be a CFD expert to use the solution. And it's integrated with other Altair solutions to make it easier for people to use the solution. On the mechanical side of the electronic system design, typically PCBs, as I mentioned before, it may go in enclosure. It may be the end product could be a cell phone, could be wearable, could be white good, for example, refrigerators, could be a dishwasher, a dryer. You have PCBs there. And these PCB, they'll be kind of, we call it, adhere to some environmental conditions. Could be vibration, acceleration, could be drop. For example, if I have a cell phone, it has a PCB circuit board inside it. As a user, my phone may drop in my hand, and it may break the enclosure, the casing. It may break the screen, but also it may affect the PCB. It may affect the component that goes in the PCB. So doing some early analysis on the product, on the system that contain a PCB, or maybe at the PCB itself, to see, for example, what kind of issue I'm going to have on this board related to vibration, acceleration, solderability. What happened to, if there's anything with solder fatigue, for example, if there's, this may be part of the assembly process. You want to study it here from a mechanical standpoint. Drop analysis. For example, if my device drop, what's going to happen to my PCB? What's going to happen to my component on the PCB? Also, we'll study the material that goes in the PCB. If I'm using one material versus other material, what's going to be the impact from a structural standpoint on the board? So there's different analysis you can do from a mechanical standpoint on the board if you want, to really try to achieve a reliable product at the end. Doing this kind of analysis, the goal to virtualize and achieve a reliable product at the end. On the mechatronic part of the electronic system design solution, of course, when designing motors, sensors, actuators, these could be a system, could be part of the system. Most of these devices, motors, sensors, actuators, we call them plants sometimes, they are driven by electronic circuit. There's some kind of electronic circuitry and PCB driving this type of equipment, could be, I just mentioned. So studying the load on these motors, the impact on the PCB, the current impact maybe on the voltage, maybe it could be the placement of the board related to maybe the motors, to study the heat effect on it. It's very important. So in this solution here, it goes beyond just electronics. It supports mechatronic design analysis and simulation, but also it will have a connection to the PCB through maybe some co-simulation into the board. On the circuit part of the electronic system design solution, in this area, we'll talk about PCB. So most of the boards, they're driven by schematic capture, driven by a schematic. driving the layout. So typically, electrical engineers, they will design the circuit and they have to analyze it. Typically analyze it maybe with some tools like mathematical tools. The most common tools is SPICE tools. This could be Berkeley SPICE, could be Altair SPICE, could be PSPICE. In this case, we're talking about tools from Altair that it's a SPICE-based solution that allow you to simulate your circuit, study the behavior of the circuit before sending the data into PCB. The last part of the electronic system design solution is the code and code generation. Some PCBs, if not most, they will have some kind of microcontroller on the PCBs. This microcontroller or microcontrollers, they may need to have some code running on them. So in this case, on this tools, in this application, will provide a solution that allow the software engineers who usually work with the EE or sometimes the PCB designers to program that microcontroller generating the C code through some kind of environment to do some kind of hardware software simulation on the PCB and the component that goes in the PCB through our environment called embed. So what's Altair Advantage? What are we talking here? As customers involved in PCB design, you may have to use different tools, different application to do your job. So you have your CAD tools, you may have to acquire some simulation tools, you may have to acquire signal integrity, power integrity, EMC tools, manufacturing checking tools, thermal tools, mechanical tools. Typically, that's what people usually do. The Altair Advantage here, the solution I just mentioned in the last few minutes, it's all sits with a single license. It's called Altair Unit. So you acquire the Altair Unit, you'll have access to all this analysis and verification environment. Even the manufacturing process. So if you're taking a design from your current PCB floor to, let's say, the shop floor to program all the machines, there's also manufacturing solution that can be provided to you guys through the licensing environment, which is I did not touch really earlier on. So what customers asking for? Most customers looking for partners. Also, most customers are looking for partners who understand their challenges in electrical, mechanical, software, architecture, design, implementation also. They're not looking for vendors. They're also looking for partners that can provide a solution that address their current and the future challenges. And most customers are looking for multiple partners. So here, for example, Altair and Altium working together as partners to help their joint customers, which is you guys. We're working together to develop a joint solution in this case to help you guys address some of your electronic design needs related to simulation. To summarize, electronic system design challenges are growing, and we need to shift left to adopt virtual testing instead of doing physical testing in the lab or in the field. Okay, bringing an integrated solution between Altium and Altair, it will help you achieve more reliable and robust products. Thank you.